So we went through and drew the possible conformational isomers for ethane, and we noticed there are really just two different energies. There is a staggered conformer, in equilibrium with an eclipse conformer. And we know that the enthalpy difference between those two is 2.9 kilocalories per mole. So we can write that delta H of reaction is equal to, in this case, plus 2.9 kilocalories per mole. The question we want to address now is what's the origin of that 2.9 kilocalories per mole increase in energy? Where's that coming from? And where that's coming from is the closer proximity of these two hydrogens in this conformer versus that conformer. When we move them into the eclipse conformation, we're actually moving the hydrogens closer to one another. That's a source of strain, and it's called a torsional strain. It's caused by the passing of two electron clouds near to one another. Anytime you get two electron clouds near to one another, since electrons are negatively charged, they're going to repel each other, and that electron repulsion is resulting in a little bit of strain. There are various sources of strain in molecules. We'll be talking about a lot of different sources of strain when we get to cyclic alkanes. But right now we have a torsional strain caused by the proximity of these hydrogen atoms. 2.9 kilocalories per mole total, but I think you'll be able to see that it's impossible to uncouple the eclipsing of those two hydrogens from the eclipsing of these two hydrogens from the eclipsing of those two hydrogens. When you rotate this molecule to the eclipse conformation, you're always going to have three hydrogen over hydrogen eclipsings, right, that you didn't have in the staggered conformer. So I know that the sum of the strain energy caused by each of those three hydrogen over hydrogen eclipsings is equal to 2.9 kilocalories per mole. There are three of them. They're equal. So if I let an H over H eclipsing interaction be X, I can say that 3X is equal to 2.9 kilocalories per mole, and thus calculate the amount of energy that it costs me to put each of those hydrogen over hydrogen eclipsings in place by simply solving for X. And just for simplicity, we'll round that and say that's approximately equal to 1. So a hydrogen over hydrogen eclipsing costs me about 1 kilocalorie per mole. It costs me 1 kilocalorie per mole there. It costs me another 1 kilocalorie per mole here. And it costs me a third 1 kilocalorie per mole here. And that's the only strain that we're going to have in ethane. But what happens when we move up to the next homolog, propane? So we actually put another carbon in place. So So what I'm going to do is I'm going to pull off one of those hydrogens, and I'm going to replace it with a CH3 group. So now I have propane. Looks like a little dog. Tail there, little nose there. So I haven't shown these. I've shown these in space filling models, right? So we have the hydrogens being quite short because that methyl group is going to not be part of my Newman projection. I'm still going to look down this bond, right? The carbon-carbon bond from carbon 1 to carbon 2. Carbon 3 is going to be sitting there. So I can start with a staggered conformation that has the hydrogen pointing down on the front carbon and the methyl group pointing up on the back carbon. Really doesn't change my Newman projection very much. Front carbon looks just like the front carbon did for the ethane, but now the back carbon has a CH3 group where the yellow hydrogen was previously. So this is still staggered. And if I rotate it 60 degrees, the same convention that I used before, where I leave the back carbon alone, and I move the front carbon, and I move it clockwise. I'll go to an eclipse conformer. Where I have colored hydrogen overlapping with a hydrogen and a white hydrogen here overlapping with the methyl group. So that's the 60-degree rotation. And I can go again. Hydrogen will have gone here. Now looking like that, where the colored hydrogen is now 60-degree dihedral angle away from the methyl group. And I can do the same thing if I want. And you should just practice drawing conformational isomers, staggered to eclipse to staggered to eclipse. So 0, 120, 240 will be the staggered conformers, and 60, 180, and 300 will be the eclipse conformers. Pink hydrogen will now be up here. And I can keep going. Putting the pink hydrogen over on the right. Conformer. Putting the pink hydrogen down here. So I go from 0 to 60, 120 back to staggered, 180 back to eclipsed, 240 back to staggered, 300 back to eclipsed, and if I keep going, I'll move that pink hydrogen back down. It'll be right back where we started. If you look closely, you'll notice that the 120 degree and the 240 degree are actually mirror images of one another. And it turns out that those are non-superimposable mirror images of one another. Also, the 60 degree and the 300 degree are mirror images of one another, where this pink hydrogen is on the opposite side of the plane. And again, those are non-superimposable mirror images of one another. We can put this on an energy diagram, and the energy diagram will actually look very similar to the energy diagram that you saw for ethane, right? We'll start with a low energy, we'll go up in energy at 60, back down at 120, up at 180, back down at 240, up at 300, back down at 360. All three of the eclipse conformers have one methyl over hydrogen and two hydrogen over hydrogen eclipsings, so they're all at exactly the same energy, kilocalorie per mole, above the low energy point. 0.3 more than the difference between the staggered and the eclipse conformer. For the ethane. So that extra 0.3 kilocalories per mole that we're seeing there between the staggered and the eclipse conformer for ethane, that must be because there's more energy associated with eclipsing a methyl group and a hydrogen. The hydrogen over hydrogen, the methyl group is bigger. By how much? Well, by 0.3. So if we rounded it and we said that it was a 1.0 kilocalorie per mole difference roughly for hydrogen over hydrogen eclipsing, we could conclude that the methyl over hydrogen eclipsing costs approximately 1.3 kilocalories per mole. It's a little bit different, right? You might conclude that it's actually 1.2 if you rounded each of these to 1. But remember that these aren't quite 1, really, right? They're really a little bit less than 1 because it was 2.9 divided by 3. So we took an estimate, right? The difference between 2.9 and 3.2 is 0.3. All of that must be because of the additional eclipsing strain for a larger CH3 group versus a hydrogen. So we can say that that's approximately 1.3 kilocalories per mole difference. But otherwise, the energy diagram for the propane looks pretty much the same as the energy diagram for ethane. So I'll end this video, and on the next one,